This meeting is being recorded.
In section 3 of chapter 14, we're going to cover one of the characteristics of our signals that's referred to as the wave number and what exactly this indicates. So the wave number, we were told in a previous video, is what is plotted along the x-axis of our spectrum when we have an infrared spectrum that's produced. So we know that our percent transmittance will be on the y-axis, and then our wave number is along this x-axis. So we have our lowest numbers over here, which correspond with lowest energy, and over here we have our highest energy. And if you recall, they go up to about 4,000 here and as low as 400. So what this is indicating here is the final product, if you will, so the wave number that's produced by this type of calculation. So you will not have to do this calculation, but this is what is being utilized to generate this wave number. So we have 2 pi over 1 over 2 pi times the speed of light. We have this force constant, which has to do with the bond strength. And then we have this reduced mass here. So really what we're going to be looking at, nothing really from this portion of the equation, but we're going to be considering the bond strength. And then the mass difference, so the mass of the atoms that are bonded together. And by bond strength, we can say, is it a single bond? Is it a double bond? Is it a triple bond? And then the mass difference of the atoms, well, is it a hydrogen? Or is it something else? Is it a carbon being bonded, a carbon to some other compound, or some other functional group like an OH, right? So depending on what atoms are bonded together, we're going to see different energies, different signals produced. And our strongest bonds, the stronger the bond, the higher the stretching frequency. So the higher our wave number, the stronger the bond. And then the larger the mass difference, we're also going to see that trend, the higher the wave number. So here are some numerical examples. So as far as everything that we discussed, so in our first consideration here, we're looking at the mass differences between our atoms. So we see that the highest signal produced is around 3,000, and that's when our lightest element is bonded to carbon. So we have a carbon-hydrogen stretch here around 3,000. And then as our atom gets heavier, so here is deuterium, this D that's indicated. So that's also hydrogen, but now we have a mass of 2 instead of a mass of 1. So now we have a proton and a neutron. So we can see that that stretch is located at a lower frequency, so around 2,200 now. And then as we add more and more mass to this carbon X bond, so now we have oxygen, we get a lower signal, and then the heaviest element, the chlorine shown here, has the lowest signal. So again, the lighter the atom that's bonded to, in this case, carbon, we're going to see the higher signal. And then in our second row here, we're looking at specifically the bond strength by comparing a triple bond. So again, we have the largest frequency, the highest wave number generated with our strongest bond. And then we see over here the opposite with a single bond to the same element. So we used carbon-nitrogen bonds to compare. So we can see that, again, that single bond would have the lowest wave number associated with it because it is the weakest of the 3 bonds shown. So here's a table that shows us some of the regions that these specific types of bonds would produce signals in. So here we have anything that's bonded to hydrogen here. So we've had carbon-hydrogen bonds that we've saw in the past, and they would be anywhere from up to 4,000 down to around 2,700. So somewhere in this range, you would see these bonds. So whatever the X is, in my example here, carbon to hydrogen. Then we have here the next highest range of energy. We see the triple bonds. Then we see the double bonds in the kind of middle of our table here. And then all of our single bonds are generally below 1,600. So this is, again, just the general trends as far as our triple, double, and single bonds and the energy relationship and the wave number relationship more specifically. And then to these light atoms, we see bonded to hydrogen specifically, we would see the highest energy produced. So this table is very useful when we're doing diagnostic, or rather when we're looking at the diagnostic regions and the fingerprint regions collectively to determine what structure we may have in our spectrum. So this diagnostic region is anything above 1500. So I'll draw that dividing line there. So this is the diagnostic region again, and this is where we'll see all of our characteristic stretching for different functional groups. And over here, this is called the fingerprint region. So mainly our single bonds will be in this region. And every compound is different in this region. So that's why it is referred to as the fingerprint region, because it's kind of like the identifier, just like our fingerprints identify us and they're different for every person, as is the fingerprint region for every compound. And generally it's difficult to analyze due to many overlapping signals and things of that nature. So we're going to focus in the diagnostic region. So let's take a look here. So if we wanted to look at these two structures and try to compare one to the other, these have very similar signals in the diagnostic region. So 2-butanol and 2-propanol in this region here, we're told they're virtually indistinguishable. So that's one of the times where you would have to venture into the fingerprint region, so over here, to really gain what compound is being present. But for our purposes, we're again going to focus in the diagnostic region. So we would be looking for, these characteristic OH stretches for the presence of an alcohol functional group, but we won't dive into the fingerprint region. But if we wanted to compare some stretching frequencies for CH bonds, hybridization can come into play here. So generally we'll see if we have an sp3 hybridized CH stretch, this would be below the 3000 line. So in our diagnostic region, rather, we would have our 1500 marker here to show us our fingerprint region. And then we have another marker that we can place here at 3000. And if we only have an alkane, we would have all sp3 hybridized carbons, and they would appear to the right of that 3000 line. If we have an sp2 hybridized carbon, like we have with this alkene here, we would have a signal right to the left. So directly to the left, so somewhere in this range here for an alkene, and then an sp hybridized carbon, so we have a carbon that's sp hybridized bonded to a hydrogen, we would see this in the highest frequency, so the higher stretching frequency for an sp hybridized carbon bonded to hydrogen. So again, depending on the hybridization, whether we have all single bonds, a double bond to our carbon, or a triple bond, so the sp hybridized, we're going to see different trends, different regions where we expect a signal. So here's a representation of drawing that line at the 3000 mark to make that more specific determination. And again, alkanes are all sp3 hybridized carbons, so they will appear below 3000, so to the right. And then with an alkene, we'll see this this signal here, this characteristic signal, shown right to the left, so directly to the left here of our 3000 line. And then far to the left, we would see an alkyne, sp hybridized carbon, CH stretch. So that's how you can differentiate if the only signals are for CH bonds between an alkane, an alkene, and an alkyne. So sometimes we know that we should have some type of signal, or we would assume that we'd have some type of signal for an alkene, so a carbon-carbon double bond or a carbon-carbon triple bond, but there are times where we do not see the signal. So what I'm referencing would be for a symmetric alkene right here, where I've circled. There's no net dipole moment between these two And there's also no sp2 hybridized carbons. So we're not going to see the 3100 signal, nor will we see in a symmetric molecule a dipole moment produced for the carbon-carbon bond. So we would be lacking that signal around 1600 for this alkene, and the one at 3100. And then over here we see our alkyne, and this is an internal alkyne, so there's no sp hybridized carbon here, right? This would be an sp hybridized carbon at the end of this bond to a hydrogen. So we won't see this 3300 signal either when we have these internal alkynes. And then when they're symmetric, like this seems to be, we would also have a lacking, rather, this CC triple bond stretch. So there are times when we believe we should have signals, but we will not. So neither of these will show those carbon-hydrogen stretches. So another consideration should be with resonance structures. So resonance can cause delocalization of electrons, and this can affect the strength of a covalent bond, and therefore the wave number that we see the stretch that results. So say we have a carbonyl, so a CO stretch, and here we have a ketone shown. And if there is no other pi bonds nearby, there's no resonance possible, we would see a ketone carbonyl stretch around 1720. Now, if we have a conjugated ketone, so over here we see a stretch around 1680. Now, the lower signal has to do with, if we drew the resonance structure, we would see a little bit of a single bond character in this CO stretch here. So we would have a less of an absorption, less efficient absorption of IR frequency at that double bond there. So because of conjugation, because we have a conjugated ketone, we see this shifted signal. So a lower signal, again, with a conjugated ketone. So this is the rationale behind that. As I mentioned, this is just a straight ketone here, no resonance possible. So we see one resonance structure possible, rather, and this would not produce a shift in our signal. But if we have this conjugation here, so this pi bond is next to our carbonyl, we have one additional resonance structure, and again, we would see this shift to a stretch at a lower frequency. So we'll continue with the intensity aspect of our signals in the next video.